Welcome to this explainer. Have you ever looked up at the sleek, aerodynamic curve of an airplane wing? Or maybe you've just admired the perfectly seamed sheet metal of your car door. Or even the sprawling, intersecting metal air ducts in a big industrial building. You've probably wondered exactly how those incredibly complex shapes were actually manufactured. Well, there's a fascinating kind of magic in manufacturing, and it begins with a wildly simple concept. Almost every complex three-dimensional object around us starts its life as a simple, flat, two-dimensional piece of material. Today, we're going to explore the precise engineering geometry behind that exact transformation. We are looking at the development of surfaces.
Here's our game plan for today. First, unfolding the 3D world. Second, 4 methods of development. Third, exploring radial lines. And finally, solving a tutorial problem.
All right, part 1, unfolding the 3D world.
So in engineering drawing, a development is defined pretty simply as the unfolded or unrolled flat plane figure of a 3D object. You're going to hear this referred to a lot as a flat pattern. Now, the absolutely crucial thing you have to grasp here is that this flat plane shows the true, exact size of every single area of the original object. And why is that so important? Well, think about the factory floor. If a flat pattern is even slightly distorted or miscalculated, what happens when it gets cut out of heavy steel? When the machinery bends it into shape, the edges simply won't meet. The seams won't seal, the bolts won't align. There's literally no perspective distortion allowed here. It has to be mathematically accurate down to the exact millimeter.
This 3D prism unfolding right into a 2D plane perfectly illustrates what we're talking about. While we call it engineering geometry, it's fundamentally the exact same relatable everyday act as unfolding a cardboard delivery box so it fits into your recycling bin. Notice how the top, the bottom, and all 4 sides lay completely flat on a single plane. Reversibility is the ultimate goal here. When this 2D pattern is accurately cut out of metal, it can be folded right along those dotted bend lines perfectly back into the original 3D object. And out in heavy industry, those dotted lines aren't just folds. They represent exactly where a massive machine called a press brake is going to apply thousands of pounds of force to bend solid steel into its final structural form.
Moving right along to part 2, 4 methods of development. When we pop open the Pattern Development Toolkit, we find 4 essential methods: parallel line development, radial line development, triangulation development, and approximate development. It's super helpful to view these not just as random facts you need to memorize, but as a complete toolkit. Why do we need 4 different tools? Well, imagine trying to wrap a basketball perfectly smoothly in standard wrapping paper. You just can't do it without getting massive wrinkles and overlapping folds, right? Different 3D shapes demand totally different geometrical approaches to lay perfectly flat. So whatever strange shape an engineer runs into, one of these 4 tools is going to unlock its pattern. Let's look at them.
Here we have a prism and a cylinder. Both of these utilize the parallel line development method. So how does it work? Imagine taking that cylinder, grabbing a pair of metal shears, slicing it straight down the middle, and literally unrolling it like a carpet. Because the top and bottom edges of a straight cylinder run perfectly parallel to each other, you can stretch the entire surface out in a straight, continuous line. The method divides the surface into a series of parallel vertical lines to easily map out the expanded pattern you see laid out right below it.
But what happens for shapes that completely lack parallel sides? We've got to pull out completely different tools. For a tetrahedron, we use triangulation. This is a method that maps out the surface using a series of connected triangles, making sure every dimension remains completely true to size. And then we have shapes like a sphere. Remember that wrapping paper analogy? Because a sphere curves in all directions simultaneously, it mathematically cannot be perfectly laid flat without stretching or shrinking the material. Think about trying to peel an orange and lay the skin perfectly flat on your counter. It's going to split. So we use approximate development. Now, approximate in engineering does not mean guessing. It means taking that highly complex curve and dividing it into hundreds of extremely thin, manageable, mathematically precise slices, kind of like the gores of a hot air balloon. So they join together to form a highly accurate sphere.
All right, part 3, exploring radial lines.
Check out this cone. Parallel lines absolutely will not work here because the entire surface tapers dramatically to a single point. Instead, radial line development uses lines that all radiate out from a single central vertex to construct the expanded pattern. Imagine an umbrella opening up. Every single metal rib of that umbrella has to track perfectly back to that common center point at the very top. If even one of those ribs was parallel instead of radial, the umbrella just wouldn't close. In drawing this development, that common vertex becomes the exact center point for drawing the massive, sweeping arc of the flat pattern you see right beneath the cone. Now, theory is great, but in the real world of sheet metal and fabrication, there are practical limits. To actually use this radial method, you strictly need two things: a radius point that is exactly on center and a radius point that is within a reasonable physical distance. I always find it pretty funny when engineering manuals have to remind us of the physical limits of our universe. One foundational text strictly notes that if your required radius point happens to be 40 feet away from your actual workbench, the radial line method simply isn't worth the effort. You'd have to literally go find a 40-foot compass, which just isn't happening. In that case, you pivot to triangulation. But as long as the radius fits on your drafting table or workbench, this radial method is incredibly fast and laser accurate.
Moving to our final section, Part 4, Solving a Tutorial Problem.
Okay, we've got the theory down. Let's roll up our sleeves and apply this to a real engineering drawing. How exactly do we develop the flat pattern of a hexagonal prism, especially one that's been cut at a sharp angle? Let's just visualize that for a second. Imagine a six-sided metal pipe and someone has taken a saw and sliced the top off at a severe slant. How do we draw the flat sheet metal for that?
Let's break down the specs. We've got our orthographic views here, which just means we're looking at the object perfectly straight on from different sides to get exact dimensions. Looking straight down at the top view, we clearly see the base is a perfect hexagon, and the instructions tell us each edge of that base is exactly 20 millimeters long. Now drop down to the front elevation right below it. This tells us the prism has a total vertical axis of 50 millimeters. But check out that sharp 45-degree angled line slicing cleanly through the top half of the front view. That is our slanted cut. The metal pipe is taller on the left, much shorter on the right. Our flat pattern has to perfectly reflect all of those wildly varying heights so that when it's finally rolled up into a hexagon, that slanted top matches up flawlessly.
To solve this, we're relying heavily on the parallel line method. Step 1 is the foundation. We draw a perfectly horizontal stretch-out line along the bottom. But how long is it? Well, the golden rule is that it must be exactly equal to the total perimeter of the base. Since our top view showed a hexagon with 6 sides, and we know each side is 20 millimeters, we do the math, 6 times 20. That means our stretch-out line must be exactly 120 millimeters long. We divide that line into 6 equal 20 millimeter sections and draw vertical fold lines up from each one. Step 2 is where the magic really happens. Watch carefully how we project the heights. We draw straight horizontal lines starting from exactly where that 45-degree cut intersects the vertical edges in our front view, and we project them directly over to the corresponding vertical fold lines in our flat pattern. Trace the invisible line from the highest point on the left of the cut straight across to the first line on the pattern. Then trace the next point down straight across to the next line. Connecting those projected points across the top creates this beautiful zigzag shape. That zigzag is the exact true size shape of the unrolled angled prism.
If you followed that step-by-step logic, boom, congratulations, you've grasped the fundamentals of surface development. And I want to show you this incredibly advanced drawing of a holed cube and a cylinder to prove a vital point. At first glance, this looks incredibly intimidating, right? It looks like visual chaos. But look closely at the flat development pattern on the right. Look at the bottom horizontal line. It is nothing more than a stretch-out line precisely equal to the cube's perimeter. It has parallel vertical lines just like our hexagon, and those curved cutouts in the middle, those are mapped entirely by projecting horizontal lines from exactly where the cylinder intersects the cube's faces in the main views straight over to the pattern. The exact same step-by-step logic we just used to unroll our slanted pipe is the exact same tool engineers use to conquer these incredibly complex intersections. The principles never change, they just scale.
It all comes back to this one idea. When the pattern is cut, it can be rolled or folded back into the original object. Whether it's a simple cereal box in your pantry, an angled hexagonal duct in a skyscraper, or a complex holed cube in an aerospace application, the strict, uncompromising rules of geometry ensure that the two-dimensional perfectly translates into the three-dimensional.
So, look around you. Which 3D objects in your life started as a simple, flat 2D pattern? The next time you walk past a metal trash can, or look up at the intersecting ductwork in an open-ceiling restaurant, or even glance out the window at the intricate sheet metal of an airplane wing, stop for a moment. Ask yourself, which method did the engineer use here? Parallel lines, radial lines, or triangulation? Because every single one of those complex three-dimensional objects protecting us and serving us started out on an engineer's desk as a brilliantly simple, perfectly precise, flat 2D pattern. Thanks for joining me on this explainer, and keep looking at the engineered world with curiosity.